Okay, so now what we're going to do is take a look at the code for the binomial option pricing model, the Cox-Russell-Rubenstein model for pricing a European call, which we've been studying for a while now, but I want you to see how the code works. And you'll see that it's set up in a kind of an interesting way. There's, of course, many different ways of getting to the same results here. But what's going to happen here is you're going to see for the first time that we have loops going through the code, which enable us to repeat something as many times as we need to get our results. Okay, so as we discussed last time, here's a problem where we have a European call option, and it's written on a stock whose current price is $100 and whose strike price is also $100. It has a year to maturity. The risk-free rate is 6%. The stock itself has no cash flows, so Q is 0. We're going to use 3 time steps to illustrate this process, and then the implied volatility, or sigma, is 16.5%. With all that information, it turns out that the binomial option pricing model produces a price of $10.14. So let's see how it did that. So first we'll go to the developer tab and open up our Visual Basic. And now I think we started to go over the constants last time. Where we left off was actually the body of the program. So just a quick review. First things first, this is a subroutine or macro, which means we type in the keyword sub. This wouldn't make any sense as a function because you only can produce one output with a function. So normally procedures that are very complicated are implemented as subroutines or macros. And so you notice all this green. When it's green, that means in the beginning you have an apostrophe, which means this is basically documentation. These are here to remind you how the program works or any assumptions you may be making, which is very helpful because in 6 months, if you come back to this program, you may not remember what you were doing here. So this is very, very helpful. Okay. So anyway, so you see here is the information about what these variables represent. And you can see, for example, S0 is the initial asset price or stock price, K is the strike price, T is the time to maturity, R is the risk-free rate of interest, Q is the continuously compounded dividend yield. Although I guess I should have, to be more consistent, I should have noted that this risk-free rate is also being treated as being continuously compounded. In the whole book, which all of this is ultimately based on, he does like to use continuously compounded rates of interest. And, you know, the reality is most derivatives models are based on continuously compounded rates of interest for really because it's more convenient mathematically, but there are other benefits as well. So in most cases, you'll see option pricing models are being implemented with continuously compounded rates, which is more consistent with the way the Black-Scholes model works anyway. So anyway, so n is the number of time steps. And you'll see later on, like you can change this. And you know, if you want to see how close this model is really getting to the Black-Scholes model, you can increase n and see how close the price gets to the true Black-Scholes price. And what you'll discover is that in the beginning, the price might not be that close. It could be pretty far off, as a matter of fact, if you only have a few time steps. But as you keep increasing it, you'd expect that we will get closer and closer. And after a while, we'll get so close that we don't even have to think about it anymore because it could be within a penny of the true Black-Scholes price. Now, the only unfortunate reality, though, here is that you don't want to overdo it here. If you try to put a huge number for n, you might find that Excel is still running a week later. So if you want to experiment with that, try to do it in small stages like 10, 20, 50, 100. Don't go in there and try 1,000 or 10,000 because you'll discover that it's going to run for a good long time before it gets to a solution. So anyway, then we have the constants. We will calculate these in the body of the program. This dt is actually what we've been calling delta t, the size of a single time step. P is the risk neutral probability of an upward movement. 1 minus P is the risk neutral probability of a downward movement. Disc is my abbreviation for e to the minus r delta t, which means the discount factor for single time step in the tree. And then We have U and D, which we've seen before. This is Cox-Russell-Rubinstein's notation. That's the size of an upward or downward movement. And of course, that number gets multiplied by the original stock price to show us where we are on the tree. Now, this is the part that we did not need until now. The indices, we're going to actually construct a couple of matrices to keep track of our information. So the I is the time step, which means it's keeping track of what column we're in. And J is the number of movements up and down the tree, which means it's keeping track of what row we're in. Okay, so in other words, what we're creating is a matrix. And so the time step, remember, if time is going forward, that means what we're actually doing with the time step is keeping track of the column that we're in. And then the upward movements tell me what row I'm in. Now, we mentioned this last time that the trees that we will create that are actually matrices are going to be implemented in a very specific way in order to tell VBA that, for example, the stocks are going to be stored as a matrix. We have to use this notation S with open and closed parentheses. Okay, and the same thing with F. That's where we're going to store this option prices. And of course, the binomial tree is a very interesting graphical representation, but it doesn't lend itself very well to computer programming. We're going to convert those trees into matrices. And then we'll use the traditional rows and columns to keep track of where we are. So we'll see that in a few minutes. And then now, of course, here the dim statement basically is telling VBA to expect these variables to be defined, although we don't have to do it just yet. And if you notice for S and F, we do have them with open parentheses and closed parentheses to remind it that these are, in fact, what VBA calls arrays. Two-dimensional arrays are what we call matrices. Okay. They also could be vectors if they only have a single dimension. Now, if you didn't notice, by the way, this statement, worksheets European call.activate, if you look at the main, here it is. Down here at the bottom, you see where the tab is labeled European underscore call. It's a good idea to tell it where to look for your information, because otherwise there could be potential problems. If you think you're on one sheet and VBA thinks you're on another sheet, that's never going to end well for you. So you can tell it, listen, I want you to go to this sheet, and that's where you will find the information that we need. Okay, so that's how you do that. You say, listen, don't go to the other sheets. Even if there aren't any, it's a good idea to tell it which sheet you want to work on. Then this, as we saw last time, this is how we read the data into VBA. Cells dot, for example, cells 4, comma 2 means in matrix notation, row 4, column 2, but in Excel notation, that means cell B4. Okay, so in other words, this one. Let's move this over. Okay. Sometimes, yeah, it'll move around all you want, and sometimes it just is very, very stubborn. Trying to move it over just to, there you go. All right, just so to make sure you can read it. So B4 would be right here. Okay, this is row 4, column 2. So the stock price is found here, 4, comma 2, and the dot value tells it that you're looking for the value, not, for example, the formatting or anything like that. If you wanted the formatting, you would have a different command. And then you're basically telling it, all right, fill in those values. Now, these are constants, so it's easy to fill them in. The vol is, I don't know why I've got that listed separately, but there it is. I just realized it's being separated here for some reason, but they're all just input statements. So all of this is basically, like the notation, the documentation is nice, but the program doesn't need it to run. It's ignoring all those green lines. That's really just to help you keep track of what's going on. But I think it's a great idea because, again, Otherwise, you might go back later on and say, I don't remember what this is supposed to mean. I don't know what I'm supposed to be doing here. So it helps you remember what all these different components of the program are doing. And also, of course, it's helping you identify the names of these variables, which if you notice, I mean, VBA is a very old language, and a lot of the variables have very short names. In fact, I'm not sure what the limit is, but it's not very big for the length of a variable name. And so you often find yourself needing to pick names that are meaningful in some way, but yet still not that clear because you only have so many letters to work with. Now here we're going to calculate the constants of the problem that we'll need. And those are the ones that we see down here, dt. Now this one is uniquely identified by the time until the maturity date of the option and the number of time steps that we chose. If I change this n to 4, you'll see it'll automatically update dt to a quarter of a year instead of a third of a year. Okay. Then we have U and D. These are Cox-Ross and Rubinstein's formulas. So just a quick reminder. Hold on. I've got an extra document here because we're going to need it sooner or later. Those were chosen to ensure that the statistical properties of the stock that we're modeling will follow the Black-Scholes assumptions. Okay, so if you want more details, we can go get the paper, the original Cox-Ross or Rubinstein paper, and go through it and where they explain how this works. But they chose this to ensure that we're actually reproducing Black-Scholes, but in discrete time steps. So we're actually creating a binomial model that replicates in the limit the normal distribution. All right. Well, anyway, and by the way, I think I've mentioned this before. This is not the only way they could have done this. They chose what they've done mainly to illustrate what Black-Scholes is doing. Later researchers found ways to tweak the model for maybe pricing other types of options that were a little bit more complicated. Stock options are fairly straightforward, but it turns out that, for example, interest rate options are more challenging. And so there may be things you might want to do differently with those types of options. Well, anyway, so here's the Cox-Ross-Rubinstein framework. And oh, yes, and we went through all of this in the slides. Here is the formula for calculating the risk-neutral probability of moving up in the tree. And of course, you recognize that right away. That we showed in the slides. And the whole point of this probability is that if we use these probabilities in the tree, it'll ensure that on average, the return to our asset is the risk-free rate of interest because we're assuming risk neutrality. Okay. So it's e to the minus r cubed dt. It's actually delta t in our notation, but VBA doesn't have Greek letters. Okay, so we saw already a demonstration of why this is correct because we were able to show that this is the only probability that is consistent with an expected return of the risk-free rate of interest. Okay, and of course, 1 minus p is simply 1 minus that, and then this variable disk, this is the present value of $1 received at one point of delta t in the future using the risk-free rate of interest as the discount rate. Okay, so it's easier usually. I mean, we could have used the formula exp minus r dt, but I find that it's easier to read the code if you use a name for it instead, like disk for discount rate. Okay. So now that's done. And so if you notice this redim statement, whenever you have arrays in VBA, even though it'll let you introduce them up here without specifying their dimensions, That can't last forever. Eventually, you have to tell it because it needs to allocate storage. How many elements will it contain potentially? So here, we're going to use 0 to n. Now, the reason why it's 0 is because in these types of models, if you notice, time is usually indexed 0 up to the whatever date we're looking for in the future. So 0 is today, 1 is one period in the future. Et cetera, et cetera. Okay. So in other words, we start with 0, not 1, but 0. Now, this is by the way, this is one of the interesting things about VBA. Many programming languages, or at least once upon a time, were unable to have indices that didn't start with 1. Like even MATLAB, as powerful as it is, couldn't do 0 indices. It wasn't designed to do that kind of thing. But you'll see as we go along that for these types of models, this is very, very helpful. Now, the time, of course, means as we go forward, but also at some point you'll see that we also have to keep track of how many up and down movements there are in the tree. But it turns out, now what's interesting about what we're about to do is that if you notice S and F, the stock tree and the option tree, only contain a single dimension. These are actually vectors. Now you might say, well, that seems a bit ridiculous. Oh my God, what happened there? No, I did not ask it to do that. So we're going to wind up with a vector that looks something like this. And you might say, well, then how can that possibly replicate the tree? Well, it turns out that for a European option, we don't actually need the entire tree because of the way it's structured. We can always take a single time step and figure out what the previous what the nodes on the previous time step must have looked like from the final or terminal time step. So in other words, in order to save processing time, what they're basically going to do is recreate a vector of prices at each point in time. So that sounds strange right now. We'll see how that works in a few minutes. And since n is 3, the reason why it only goes up to 3 is because n is 3. And when we're done, the stock price, I mean, sorry, the option price that we're looking for will actually end up being right here in F0. Because in the beginning of the tree, there is only one element, or one node, I should say. So we have to visualize that we're creating a vector which will repopulate at every point in time, starting with the maturity date of the option and working our way back to the present. So we're actually going backwards in time when we populate these trees. The reason why we have to do that is so that later on when we price American style options, we have to have the ability to stop and say, listen, does it make sense to exercise this option or not? And that's only possible if we have the future time steps already calculated. So anyway, we'll get to all this later on. I just want you to see that as far as the program goes, you're just defining a couple of vectors and we will fill it in a very specific way as we go along. So for now, though, it's enough to tell it that it has elements 0 through n. So if, again, n is 3, that means the indices will run from 0 to n. Okay. Now, once it's calculated our constants, it prints them out on the spreadsheet. Okay, so 13.2 is row, that would be B13 is where we put DT or delta T. And then so on and so on. In other words, they're all going to end up being printed. That's only, by the way, that this part isn't absolutely necessary, but the reason why I like to do this is because if something goes wrong and you're not sure why your program is not working, one thing that might have gone wrong is you may have inadvertently incorrectly programmed the values for one of these constants. And if that happened, you would recognize it right away when you see these on the printout. Okay, that can be an easy thing to do. You make a typo and suddenly your formula for P is a little bit off. This is how you know. You look at it and say, wait a minute, what's going on here? All right, so now we get to see some actual code. Now, this is where I have to start thinking about what it's doing. We'll start with the stock tree. So what we have to do is visualize what we're doing here. We're taking a lattice. So we haven't seen a three-step tree before. It's not that much more complicated. Okay, so these are the times 0, 1, 2, and 3. So the what we're calling US DS, or actually it makes no difference whether we call it DU or US or DU or DS. Let me just go back and visit the slides for a tenth of a second. I just want to be consistent. Okay. See, some books will write down the stock prices as US, DS, that type of thing, and others will do it the other way around. So I just want to make sure we didn't. Okay. So I'm going to change these two to SU and SD. Like I said, it doesn't make any difference. And we're going to actually fill in a matrix, sorry, vector, with these values first. And they will be referred to as S0, S1, S2, and S3. So in this context, you can think of the index like this 0 means no upward movements. Okay, so the index or S refers to the number of upward movements since the initial time step. Okay, so in other words, SD, oh, I just realized I labeled this incorrectly. This should be SD cubed. There, that's better. So in other words, SD cubed means that we went down 3 times in a row. Okay. Or think of it as we haven't gone up yet. I have to move this now. So in other words, this is, so when you see S0, it means that we must be at the bottom of this vector. Now in time 3, that would mean we're at SD cubed. So right now we're in time 3 in this, we're going to fill in time 3, then we'll work our way back to 2, then 1, and then 0. Okay, so we're going from right to left, or in other words, backwards in time. So what we need to tell it in the code is that S0 in this case is equal to the same thing as going down that many times. So since this is the third time step, it's going to say in the code S0. Now remember this is S, this is the matrix or vector, I should say, S0, not to be confused with this constant S0, which was the initial stock price. Okay. Sometimes in some books they call it just S in the beginning. Sometimes they call it S0. The book we're using likes to call it S0. So don't be confused by that. This means the starting value of the stock. And so what it's saying is multiply that by d to the n power. So since n, remember, is the number of time steps, which is 3, what this is saying is S0d to the third power, because n is 3. And that's exactly what we want. Okay. So then the question becomes, what do we do about S1, 2, and 3 here? All right, well, here's the interesting part. And this is one of the consequences of the way this tree has been structured. S1 is SUD squared. S0 is SD cubed. If you take the ratio of those two, you'll see that it's equal to 1 over D. Oh, sorry, no, it's not. It's equal to U over D. Okay, sorry about that. Let me fix that. Okay, now if you do the same thing with S2 over S1, okay, let's come up here. S2 corresponds to SUD U squared D. S1 corresponds to SUD squared. And again, oh my God. Oh, how do you like that? So in other words, if I wanted to know the value of S1, algebraically, I multiply S0 by U over D. And the same thing will be true for all of them. Okay, in other words, S2 will be simply S1 times U over D. S3 is S2 times U over D. And that's because, and now this is only possible because of the way the U's and the D's are inverses of each other, where going up and then down is the same as down and then up. This is one of the many advantages of the Cox-Russell-Rubinstein framework. It makes it pretty easy to code it. So in the code, if you notice, we've got our first loop. Okay, now, first things first, there are two indices going on here, I and J. So I'm going to copy this into here. So we can make it a little bit bigger. So in other words, what we have to think about is J is the variable that keeps track of up and down movements. In other words, what row are we in a matrix? So that means S0 tells me that J is 0. S1 means J is 1. And S3, J equals 3. So if you notice this command for J equals 1 to N, what they're going to have us do is let J repeat, move, goes from 1 up to n. And when it reaches n, we stop the loop. Okay, so when we're in the loop, Sj is Sj minus 1 u over d. And also, by the way, VBA is very particular about its loops. If you have a for statement, you have to finish it up with a next statement. Okay, so now let's see if we can reason out what it's doing. So j equals 1 initially. We enter the loop. So it's saying SO1 equals S0 u over d. Fine. We just saw that that's what it's supposed to do. Then when it goes to the next statement, j becomes 2. And then we have S2. It's blocking my eraser here. It's S1. And you notice how it's J. This is supposed to be Sj. This is Sj minus 1 times u over d. And then it goes to the loop again. J equals 3. S3 equals S2 u over d. Now, when it hits the next statement again, it will not continue because j has already reached the limit, which is 3. It can't go on to j equals 4 because n is only 3. So within the body of this loop, it did 3 things. It solved for S1, S2, and S3 using j as the index. And what it basically said was wherever you are now, take the previous value of s and multiply it by u over d. And that's what we did. Okay, based on what I showed you here. So this is a classic VBA loop. What's important about it is that you have to tell it how many times to repeat this. It doesn't know. You have to tell it at 3, 5, 16, whatever it happens to be. But if you notice, all the variables inside of the loop are being referred to by J, the index. That's how it knows what to do. All right. Now that doesn't, now, by the way, you can have as many statements here as you want, but at some point, the value of something has to be related to J in this loop. Otherwise, there's no point. And so what it did was it filled in the stock prices for the maturity date, which corresponds to time 3 in this model. So these others have now been filled in, and they now contain what we are thinking of as these values. So now we have the stock tree, but only at time 3. So you might say, well, that's not good enough, is it? Now, here's where we fill in the option tree. And as we know, when we get to that last time step, the price of this option is nothing but the intrinsic value, meaning the payoff. Now, remember, this one is a call. Oh, you have to be careful with this thing. This tablet, I mean, sometimes it gets away from me. All right, so now that we have our stock tree, or what I should say is not the tree, but the nodes at time 3, that would be more accurate. These are the terminal nodes. Actually, I'll tell you what, let me make this a little wider. So corresponding to that array or vector, we have something like that going on now for the option, which in this case is a call. And so actually, I'm going to need even more room than that. Hold on. So it's called F0 here. That, I guess, let me do this. Quickly remind you that we would have called it FDDD. And so because it's a call, it's simply the max of S D cubed minus K and 0. This one is what we would have called FUDD. Here it's called F1. Yeah, I'm just filling in the intrinsic values. This one would have been known as FUUD, but here it becomes F2 rather. And then at the top, we'd have this. So the question is, how is it filling these in? So remember, the index that we're using here is J to represent moving up and down, or in other words, the rows that we're in. So what it's going to do in the code, it's going to start a new loop, J, but it goes from 0 to capital N, meaning from the bottom to the top, because all four of these are done the same way. So if you notice F of J, which means F is 0 here, then 1, then 2, then 3, and then it's got, well, what do you know? If you recognize that, application.max. Now here, this is simply the Excel's max command, maximum. We need the keyword application to remind VBA that this is an Excel command. And this part we recognize very well. It's the max of S minus K and 0, but instead of referring to it as S, we refer to it as S of J so that it knows that this SD cubed is coming from over here on the left. So in other words, it's thinking of that as S of J. So that J is how it knows which stock price are we looking at. All right. So also keep in mind that as we go along, J equals 1, 2. Actually, I'm sorry, 0. It starts at 0. For both trees. So the J starts at the bottom at 0 and goes up all the way to the top, which is capital N. So that's how it knows to fill it, this is how it's able to fill in the tree correctly. And then when it goes, if you notice, it's from 0 to N. So it goes to it fills in the entire vector in this loop. And now this is where we are now. So what we've accomplished is we filled out the trees at time 3, which is the terminal date. Now, this is where it gets really interesting. What about the previous time steps? What about time 2 and time 1 and time 0? Well, this is what they're going to have us do. Let me first just go ahead and draw one of these again. Or sorry, SU. Let's do SU. Just to be consistent. And while we're at it, I think I'm going to run out of space. Here we go. And then, yeah, we need one more time step. Hold on. So basically what we want to notice here is that we're going from this back to this. Okay, now again, this is if this weren't a European option, we couldn't do this. When it comes to the American options, we'll need the full tree at all times. But here, it turns out we don't really need to keep the entire tree stored because watch what happens here. We're going to line these up side by side. So again, here what matters is the value of J. So remember, here J equals 3, 2, 1, and 0. So here we had SD cubed. Now here, J equals 0 will be the bottom again, SD squared, meaning no upward movements. And then J equals 1 will be this SUD, meaning one upward movement. And then J equals 2 will be SU squared. And guess what? There is no value here because at this point in time, there's only 3 nodes. So in order to figure out what this vector should look like at time t equals 2, you'll notice a very interesting relationship between the 2 time steps. So what is that difference? Is that basically when j equals 0, time step 3 has SD cubed, time step 2 has SD squared. Ratio is always D. Okay, in other words, to go from here to here, actually to go from here to here, actually I should have written it the other way around. Let's put T2 over T3. So at j equals 0, we multiply by a constant. Now let's see if that's true at j equals 1. What do you know? It's always the same. And then at j equals 2, which is the last one. Whoops, I wrote the wrong thing. Sorry. So here, SU squared over SU squared D. Huh. It's uncanny. So in other words, that's the relationship between all of these nodes at the 2 time steps. If we line them up according to J, the number of upward movements, you can see it's an easy transformation. So we're going to create a loop. We're going to go through all of these only up to J. In other words, we have to make sure that the loop knows to stop here, though. And then each time it's simply taking what it had in the previous case and divided by D. So, well, it's not so obvious, but that's exactly what it's going to do. Now, it turns out that even that, what I just showed you, is not absolutely necessary because since there's no early exercise, we don't even have to bother filling in the stock price tree. All we have to do is fill in the option tree. And we can actually basically ignore the rest of the stock price tree because this connection is so straightforward, we can figure out what we need from the final time step. We don't even need to bother show what I just did with you, filling in these. So instead, we'll take our option tree. So I'll just quickly fill these in. This would be SUD squared. All right, looks like I didn't leave enough room here. So here's what we want to know. Let's just visualize this from the tree. Do you remember this from last time? Let's say I pick FU as my node. You'll recall that FU is determined by doing the following. First, we have to discount the present value of the expected value of F in one time step. That's what this is. So that means that whatever goes here, this F0 will be the discounted value of, and I definitely don't have enough room here, but we're going to put P times what is currently being referred to as F1 plus 1 minus P times what is currently being referred to as F0. Because this is F UDD, and this is F DDD. Oh my God. Now that's the tricky part. You're basically in effect, reusing the same cells. So, and yeah, let me just remind you that this is actually what we would have called FDDD, FUDD, FUUD, and here we would have had FUUU. So we're going to go through the entire group. Now there won't be anything up here. F1. So this will be PF2, 1 minus PF1. Or in other words, this is F U U D, F U D D, and then finally F2. No, it's getting a little messy here, but so you're doing the same thing each time. You're basically saying, well, what's coming next? Figure out the expected value, multiply P by the node that I get when I go up, 1 minus P times whatever I reach when I go down. All of that is combined and then discounted by e to the minus r delta t. And when that's done, then we step back to the previous time step and we stop when we reach today. because at that point, there's only one number left, and that is the option price. So now this is the most challenging structure we've seen yet. This is what we call a nested loop, a loop within another loop. So because this is getting very, very complicated, we'll have to pick it up again next time right about here and maybe refresh your memory. But I just want to point out that you can have what are called nested loops. But by the way, when this is done, we'll be in pretty good shape for understanding how to do the European options. The Americans only really require one or two small changes, but we'll do that next time. Right now, I just want you to see how this one works. So you've got I, which is our time step, and it's working its way backwards to the tree. From time 3 back to 2 to 1 and then to 0. Within each time step, it's going from the bottom of the tree to the top. Okay. And so this is what I was just showing you. Okay. Yeah, these calculations right here. So and you notice the I goes 0 to, oh, by the way, I almost forgot to mention this. If you're going to go through a loop backwards like this, there's a command you have to use called step -1. Okay, so in other words, if the loop goes from 1 to 3, that's fine. But if it's 3 back to 1, you have to use this extra command here, step -1, to tell it you're going backwards one step at a time. Okay, and then you need 2 nexts, one for each of these 4 loops. And so I'll tell you what, why don't we do this? And this is a lot to take in at once. We'll stop here. Next time we'll pick it up right here. We'll write some actual numbers in so you can see what's going on. And then finally, when that's over, then we can see how this would work for the American versions of these options. Then we can move on to the trinomial trees, where it's kind of an extension of this, except that you have to allow for 3 time steps. I'm sorry, 3 branches. And you'll see that while that sounds much more complicated, in a way it's not, because the structure of the tree is actually easier to program in VBA because it's more like a matrix. Okay, here we have a lot of choices to make. We have decisions to make because you can see it isn't nicely lined up, but the trinomial tree is nicely lined up. So we'll see how that goes. All right. So hopefully this wasn't too overwhelming, but like I said, we'll go over it again. And this time we'll fill in some numbers and then you'll see where the results came from. Okay. In fact, what I'll probably do is pop it into Excel, except not just the code. I mean the actual example, so that at each node the formula will be sitting there, so you can look at it if you want. Okay. So anyway, so I guess we'll stop this right now, and then when we pick it up next time, we'll wrap this part up and then see how this works with American options. All right. So I'll see you next time.